primitive way of drilling through rocks. People using very creative methods. For example, hitting the rocks with fire and then treat with cold water to shatter the rocks. That certainly improved the efficiency of breaking down the rocks into smaller pieces and make water channels and etc. The Roman Empire used a very similar method. They tried to heat up the rocks and then cool them suddenly or quench them by using cold water. People also in the ancient time used the machine drill. So I think let me try to see whether the video works. So that's a representation of machine drill. Right, so the setup is ready. You need a bow and a string, and the drill bit is a piece of rock that people were used to use these reciprocal motions to move the drill bit back and forth for drilling holes through wood and stones, and also for getting fire. So this is another primitive technology of drilling. We call this pump drill. It has a history about 3,000 years of this technology. This pump drill use a flying. If you paid attention earlier, that they have attached a flying stone on the drill, so that they will increase the momentum. Right, increase the momentum of that drilling process. These are very efficient technologies for drilling. They use back and forth motion of the drill bit, which is very low efficiency overall. Fast forward to the 17th century, we began to use how to use gunpowder to do rock blasting, and the first modern rock drilling machines started probably back to the middle of 19th century, and people used that to drill the first tunnel across Mountain Alps. So that's the modern way of drilling. People begin to use rotational methods to do drill around the same direction rather than back and forth. If we look at all the modern drilling technologies, they can be generally grouped into three categories. The mechanical methods, they use rotary or hammer drill, or use blasting a liquid with small particles in it to do erosion type of things, and drilling. Explosive excavation, thermal drilling, using either different techniques to generate very high temperature, or use liquid nitrogen to contract the rocks and generate cracks and drill, or use chemical method, very low pH acid fluids, but not typically working well for rocks. Anyway, so that's the modern drilling methods. I think drilling is very important for civil engineers. Most of the subsurface infrastructures, including all the tunnels, sewage and water supply systems, and underground utilities, are actually made by drilling. If we look at oil and gas industry, first of all, most of the energy we use nowadays are coming from subsurface, all the oil, gas, and coal, and etc. They are coming from the subsurface. They provide more than 80% of the energy we consume in US. With the depletion of all these natural resources, we can see that the drilling depth increases with time. So the figure on the right shows the average drilling depth in United States, and we can clearly see that we are drilling to a greater depth to have access to those resources at a greater depth. And each of these drilling wells will cost $1 million, a few $1 million each. So quite expensive activity we do to recover the energy we need. So, all right, so I average around $5 to $8 million per production well onshore, and the offshore cost will be sometimes will be even higher. So if we look at the future energy, clean energy from subsurface, like the enhanced geothermal systems, the drilling is very expensive simply because the drilling efficiency is very low. It's very hard to drill through very abrasive rocks at high stress, high temperature conditions. They just cannot cut the rocks efficiently. Now, this figure illustrates the cost associated with recovering enhanced geothermal energy. There was geothermal energy from deep in the ground. So the drilling really cost a significant part of it, and including all these earlier planning costs and etc. If anything, if the drill string or drill bit fails, then it will take extensive time to replace everything. So that comes with a high cost as well. Deep sea coring, we work on gas hydrate, and we do core these sediments from deep the oceans, and efficient drilling is is a challenge for drilling through not only high rocks, but also through these granular sediments. All these small particles can get stuck in lots of different rotary or screw systems that can fail the drilling eventually. For NASA to exploration in extraterrestrial conditions, efficient drilling is very challenging. You have less access to these local resources that can help you to drill efficiently. And in fact, the most recent failure of the mower sensor, they just could not make it penetrate into the soil. They try to use different methods trying to bury a sensor to about 1 meter underneath the ground and to collect all the temperature and thermal information, and they couldn't do it. So there are many other activities that are quite relevant to drilling, including the technical drilling and medical applications, and etc. So we cannot emphasize enough of the importance of drilling. And in overall, drilling is really challenged by the efficiency we are facing for subsurface, particularly the failures of the equipment, and the ROP rate of penetration is very low. So that's some of the general background of drilling and drilling practice. So that's shift the gear to talk about the holes in the rocks, or the Angelwings. I assume some of you may have seen some of the stones on the beach or on the next to the pond that have lots of very smooth holes on it. Not sure whether you wondered what causes these holes on the beach rocks. They're actually drilled by clams. There are different types of clams. They can drill through very hard rocks, and in general they call the piddocks group. So there's one particular type of piddocks group is called Angelwing, and that's the one that on the lower right, and that's the one that we are studying. It has very delicate shells, very thin shells. If you look at the shell itself, it has very symmetric structure and very beautiful. And when the two shell valves opens up, it looks like very similar as Angelwings. So that's how they gave the name. And if we take a closer look at the surface, they have all patterned nails at the surface. We call that denticles. It is, in fact, these denticles that can make efficient cutting and breaking of the medium. So if we cut the shell and look at the profile, you can use a logarithmic function to perfectly fit the curvature of that. So there must be some geometric or morphology advantages to give the shell a good overall structural strength, although the material itself is relatively brittle. So that inspired us to study how exactly this shell can drill through hard rocks. So in the next section, I will try to focus on the three aspects we've studied in the past year and a half, looking at the morphology, the morphological advantages of the shell in drilling, the shape of the denticle, the shape of the nails at the surface, how that may impact the efficiency of cutting, as well as the material characterization, what are the chemical and mechanical properties of the shell itself. Okay, so let's start with morphology. Prior introducing the morphology, I have a short video to share to introduce the Angelwing Clam as well.
Okay, now here's something really, really cool. There's a little hole here about the size of a nickel, and inside it I can see a little siphon. And I think I know what this is, but this one I'm going to dig up by hand. Boy, this is mucky stuff. I mean, there's all kinds of nutrients and stuff in here. I mean, this darker mud is from lack of oxygen. Boy, look at the tide is rapidly coming in, so we got to do this quick. Just in the nick of time, because the tide water's getting very deep. But look at that. So this is an Angelwing Clam, and this is the siphon. So this is the thing that was sticking up out of the top. And I mean, this thing was, this deep in the sand. And so, boy, talking about an amazing creature. Very delicate shell. Since this guy lives underneath the sand, it doesn't require that real hard shell that a lot of other bivalves have. You've probably seen these as, shells. People collect these for the shell trade. And also, in other parts of the world especially, people eat angel wings. They're supposed to be pretty good to eat. But since it lives underground, it's well protected from a lot of things that might want to eat him. And believe me, a lot of meat on that. So there's a lot of things that would probably want to eat it. Okay, let's put this guy back in, and I'll tell you what, the tide is coming in very rapidly. So we want to get out of here so we don't get covered up.
Okay, so that's a video clip I find online. So that probably will give you a good introduction of what Angelwing Clam looks like. We studied this to find a new solution for efficient drilling, not really for meat. So the first thing we did when we started the project is to get a three-dimensional imaging of the shell, so that most of the Angelwing shell will have a pattern like this. They will have the concentric ribs. On the concentric ribs are those denticles, or those layers. They have the anterior, that's the front, that's the end that they're going to penetrate into the rocks. They have the posterior, that's the back, and they have also the dorsal side, the back side, and the ventral side, and the belly side. So the concentric ring will expand as they grow. They also have radial ribs. Those radial ribs will extend as well. The number of radial ribs is fixed. So typically most of the Angelwings will have 26 to 28 radial ribs. The one shown here has 27 radial ribs. So if we zoom in again, we can see all these denticles that are located on the radial ribs and concentric ribs. And if we take a further close look up of these denticles, they have this shape very similar as our fingernails, and they also have precipitated calcium carbonates that to support these nails. Inherently, all these nails are also calcium carbonates. We will introduce that in a minute as well. So but they still, even with calcium carbonates, they will be able to cut and break very hard abrasive rocks. So once we have the three-dimensional CT scan, we can exactly pinpoint the location of the denticles as well as the geometry of the radial and concentric ribs. So you won't develop a mathematical model creatively using only 4 parameters, theta, eta, phi, and beta, to describe the radial ribs, then plus 2 constants, A and B, then we would be able to mathematically describe the three-dimensional morphology of the shell or the shape of the shell. Then on top of that, we have the denticles that are sitting on these ribs with 2 additional directional parameters. We can then fully capitalize the orientation of the denticles as well. Now, if we have a mathematical model to capture the shape and the orientation of the denticles, then we can do lots of mechanical analysis, very simple mechanical analysis to look at, for example, what will be the stresses, the torque, and etc. during the advancing motion when the shells that are advancing or drill downward into the rocks, or during the borehole enlargement. So when typically when they do the grinding, they will use their internal muscle to attach against the inside wall of the hole, and then do rotational movements to scratch the materials in the hole. They can also have other motions to do borehole enlargement. So we look at all these different motions when they drill through rocks and calculate the stress distribution and also the overall torque they will use to drill. We also look at the overall geometry. So if we look at the ratio between the overall length versus the width, we call that an aspect ratio. So if we have a low aspect ratio, that means we have a relatively shorter length. So we call that a round type Angelwing. And if the length is relatively larger than the width, the aspect ratio is high, we call that a P-type, a pointy type. And there are literature in Japan that reports where you can find the round type versus the pointy type of Angelwings. So in relatively soft stones, you can find more of these, the most mud stones, you can find more of these pointy type of Angelwings, while in relatively hard stones, you find more of the round type, the Angelwings with a relatively low aspect ratio. So we use our mathematical model to calculate the torque they need to do different types of drilling. And you can see that for a round type, they actually need much less torque or work to drill. While if you have a pointy type of a structure, then it will take extra efforts to drill. So that's so in other words, if their living environment has abundant harder rocks, the round type of Angelwings will take less effort to drill and survive from predators. So if we look at the cross-sectional profile of that, and you can use a very smooth logarithmic curve to curve fit the profile. And the logarithmic curve requires 2 parameters, A and B, and theta is the angle in reference to the original point. A is a scalar, and B describes the rate of changing in the radius, the rate of changing in radius, right? So that's the logarithmic equation. So if we look at all the radial ribs, that actually describes the radial ribs as well. If we look at the radial ribs, they have different length, they have different A values. They also have different rate of expanding the curves. We call that B values, right? So that's the B values for the 27 radial ribs. So it's roughly around 0.6. It's roughly around 0.6. There are some values that are higher, as high as 1.5. It means they can expand. We use a pointer. So that means the curve can expand at much faster rate with a longer length, or they have relatively low value. So on average, the values is around 0.6. Now we we then did very simple analysis, comparing a log spiral shaped of a rib versus an elliptical shaped of shell, assuming that the shell going to expand or open up and begin to remove the materials, considering the we have to make assumptions like linear elasticity of the materials and etc. We calculate the amount of energy they need to rotate the shell for 1 degree C, and how that work, normalized work, is going to change with the B value. Again, B reflects the rate of the change in the spiral curve, and the results shows how the B versus the how the B value change will affect the amount of work to do 1 degree of rotation by compressing or removing the materials. And the log spiral shape, the amount of work they need will decrease dramatically. But at the same time, if the B value decreases, that means the space underneath the shell will decrease as well. So that's a living space, how that will change with the B value change. Right? So we do want to have a larger B so that when they do drill, they will need less work. But of course, underneath the shell, the tissue need to grow. So we do want to have a certain living space there. So with the B value around 0.6, that probably give us an optimum space we want to live, as well as the reduced workload. So talking about work-life balance, I think Angelwing gave us a good bio inspiration there. Okay, so that's the morphology. Then if we take a look at the denticle, we look at especially the denticle shape and how the shape of the denticle affect the drilling or the cutting efficiency. Now, in the lab, when we evaluate how easy to cut a material, how easy to remove the materials from the surface, we can do a scratching test or indentation test. We did this numerically in the lab, as well as some of the physical testing. Okay, so what we did numerically is using DM models to look at the cutting or scratching efficiencies for different shapes of the cutters. We have a plate shape of cutter, we have a elliptical shaped, as well as a half circuit shape of cutter, which is very similar as the curvature of the denticle here. So the one shown here is a 3D X-ray imaging of the shape, and we carved the denticle out and plugged them into the DM simulation and look at the scratching process of that of the denticles as well. Now, most of the results were presented in the following two ways. The one on the left shows the broken bonds or the removed particles, and as the cutter, either a plate cutter or a half circle cutter, that they scratch through the surface. The color indicates the time as the time progresses, or as the scratching progresses along the surface of the sample, they will remove the particles. On the right, we show the forces they need during the scratching process, the number of removed particles as the scratching progresses, as well as the number of broken bond, the number of particle-to-particle contact will be broken. So that will be the results. Now, let me quickly show some of the results without showing all the details. Now, here shows the result contrast. If we have a platey type of cutter or scraper versus a half circle type of scraper going to scratch the materials. So these two figures shows as the scratching progresses, how the material will break. If we look at the top view, we can see that all the materials that were removed will have a similar, they will leave a scratching mark there, and the scratching mark has very similar width as the width of the plate. However, if we look at the half circle, the width of the scratched marks are actually slightly wider than the half circle, slightly wider than the width of the cutter, right? So we can see that there's a kind of expanding failure as the scratcher going through the surface of the material. Right? So we can see clearly the shape will affect the number of the particles we remove and also affect the scratching marks they left at the surface of the rock. On the right, we can see the contrast of the forces they use. If we have a plate type of a scratcher, the initial force they need to do the scratching is slightly higher than that of the curved surface. And likewise, if we look at the removed number of particles, the plate one will need a higher force, but remove less amount of particles compared with a curved scraper or a curved cutter. There's another aspect that is important for the efficiency of drilling is called the rake angle. So the rake angle is defined as the angle of the cutting surface relative to the work, relative to the rock or the specimen we want to cut. And we have a positive rake angle versus a negative rake angle. And we do explore how that will affect the cutting efficiency. And as shown here, if we have a negative cutting angle, it is more like a dull cutter shape. You will need a higher force and then remove less amount of materials. If you have a relatively sharper cutter, that will need relatively smaller force to do the cutting and can remove more materials. And of course, there's a disadvantage of using a sharper cutter, that is the damage at the front of the cutter. The sharper angled cutter can be damaged much quicker than a dull cutter. All right, so you do have to balance the efficiency of removing materials versus the damage of the cutter itself. We also look at the impacts of the material properties. If you have a more brittle material versus a ductile material, we can track if you have a brittle material when we scratch at the surface, how much of the particles will be broken in tensile failure versus the amount of particle that will be broken in shear failure. If we have a brittle material, most of the failures will occur by stretching the particle-to-particle bond and break them in tensile modes. While if we have a ductile material, like a Play-Doh to an extreme case, most of the failure at the contact level will be dominated by shear. And we do also look at 4 different materials, brittle versus ductile, which shape will work the best. And for brittle material, the cutter with the curvature at the surface will be more efficient in removing the materials as they scratching through the surface. They also leave a mark with a width that is larger than the width of the cutter. While for plate, it is less efficient. Here we are plotting the displacement or scratching distance versus the cutting efficiency, which is defined as the number of removed particles normalized by the force they take. However, if we are talking about a ductile material, like Play-Doh to an extreme, that the plate actually works more efficiently than any curved surface. So if we look at the stress distribution on these cutters, for plate type of cutter, we can see lots of stress concentration at the bottom, especially at the edges. That's where the cutter will be damaged, or the cutter will deteriorate as the cutting progresses. However, if we have a curved surface, most of the stress concentration will be at the very front of the curved structure. So that will help to protect the integrity of the cutter, because the edges, where they will be easily broken or have higher stress concentration as those in the plate, won't be a concern for a cutter with a curved surface. And the curved surface has very similar results, or the identical results. We actually plug in the CD shape of the identical and do the simulation. We look at also the rake angle, the back rake angle, as well as the side rake angle, and how that will impact the results. Most of the results we obtained for the identical cases are very similar as those results of the half-circuit identical. So whatever the benefits we saw earlier in terms of half-circuit cutter versus a plate circuit, they are applicable to the identicals of the Angelwing here. So we do see that with the curved surface, they help to minimize the damage during cutting, as well as they can leave a relatively large scratching mark than the width of the identical itself. And also the cutting angle of most of the denticles are around 15 to 45 degrees, so close to 30 degrees of optimum rake angle there. We also look at the synergy. If we see all these cutters, all these denticles, they are gapped with a certain distance. We look at, for example, the cases that if we put two denticles together, too close with each other, 1.5 millimeter, they will have, and they move simultaneously, they will remove the particles along the cutting path. They also over-crush any particles in between. However, if we leave the two denticles separate apart, and the two scratching marks do not interact with each other, then the two will act independently. There's a synergy, or there's an optimum distance. There's an optimum distance between the two denticles if they are scratching simultaneously. That can give you a better performance. So the relative distance between the two cutters are also very important. You do not overcrush the materials in between. You do not want to the two separated too far away, so that each of the denticle will act independently. So you do want to control an optimum distance that can give you the maximized cutting efficiency. So that's what we see here in the results, and as well as in the actual Angelwing denticles. So if we move to, so that's, oops, my slide is frozen here. I hope you can still hear me.
Yes.
Okay, good. My slide is frozen here, so give me a few seconds. I apologize. Well, I think the next section is to discuss about the material characterization. What are the chemical compositions of the shell and the denticle, and how does that compare with other calcium carbonate material we find in literature, and etc. Oops, I think the file is probably too large and my computer is frozen. There you go, the shell material characterization. Okay, so if we look at the material under the SEM, so that's the profile view. So that's the inside of the shell, and that's the outer side of the shell. And these extruded points are actually part of the denticles. So that's the SEM images at the top of the denticles. They have relatively smaller particle size and different morphologies. And these are the photos that are taken in the middle section of the shell, and those are photos taken at the bottom part of the shell. Certainly, if the crystal size is very small, we can see a very polished, very smooth surface. And if the crystal size are longer, we can see a relatively rough surface. We can also polish or remove the materials that is perpendicular to the shell, parallel to the shell, perpendicular to the denticle, and we look at the crystal morphologies and etc. here are a few additional ones. So that's the shell outer side, and that's the shell inner side of the shell. That's actually a denticle. That's a broken denticle. Anyway, if we zoom in to look at the middle part of the shell, they have kind of braided patterns. And if we zoom in, they all have very different structures. They all have very different structures that can make them stronger. We took them under XRD and EDX and look at the mineralogy and element analysis. They are abundantly calcium carbonates. Majority are calcium carbonates. Somewhere in the denticle, you may find a little bit of potassium, but not quite typical, or a little bit of silicon, but not quite typical. Majority of them are still calcium carbonates, but they have different forms or polymorphs of calcium carbonates. We know that there are three popular forms of calcium carbonates: calcite, which will precipitate in large crystals, or aragonite in more like longer, slandered crystals, versus vaterite in platy structures. And we see all of those in the earlier SEM, images. So we wanted to understand the material properties, and the way to look at the crystal level material strength and mechanical properties is through indentation. So we run some of the Nano-Indentation test. The test is relatively simple. You need an indenter, which typically will have diamond at the tip. You can have different shape of the diamond. You can have a semi-spherical or prismatic, or even a triangular shape of a tip. And what you need is a sensor that can measure the load when you make an imprint at the surface of the material. So a typical indentation test, the results of a typical indentation test is shown on the right. You do the loading and monitor the deformation of the material. Then at a targeted load, you hold the load constant, allow the material to creep. That will give you information of the creep properties of the material. Then you can do unloading and then monitor the elastic deformation recovery. And of course, you will have a permanent plastic deformation there, right? Through this loading, unloading curve, you can get properties like modulus, elastic modulus, because we assume the unloading is purely elastic. And based on the load you applied and the volume the created during the indentation, you can calculate the hardness and etc. So if you can take a high resolution SEM image or a high resolution microscopic image, and you can see any crack development, you can estimate the fracture toughness as well. So that's an indentation test. Now, because of the small area, this is a very small scale, right? So the scale bar probably is not clear. The scale bar here is only 10 microns. So you can see that apply only 1,000 millinewtons. So that's 1 Newton of force, and that will penetrate into the specimen to 2 microns, 2.5 microns, right? 1 Newton of force is very small. It's very small. It's like the weight of an apple typically will cause, right? A weight of apple will give you 1 Newton of force. So that's a tiny force we play. Since the most of the stress are concentrated in a small area, so you still be able to deform the rock surface and get the material properties measured. Okay, so here I show some of the here I show some of the indented marks at the denticle tip. Oops, I think I'm frozen again. If you have any questions, this may be a good time to ask any questions as well.
Yes, you can. We have connected with the okay, the open.
Yeah, hi, Sheng. This is Rich Rigero.